Hi, my name is Eva, and this is my third lab for Physics 2 about circuits. A little introduction to what this lab was about is we used like an online, like virtual circuit kit to predict how circuits behave with resistors in series and parallel, and then we looked at it in the model. We measured and interpreted current and voltage values using a multimeter, investigated the properties and behaviors of ohmic resistors and capacitors, and explored how voltage changes over time as a capacitor discharges in an RC circuit, and determined the time constant of the RC circuit. So I looked at some of the laws that we looked at in class, like Ohm's law and Kirchhoff's law, which I used in my calculations later in the lab. So the overall results of what I did in the lab were that voltmeters have high internal resistance, and this minimizes the current draw, and capacitors don't charge instantaneously. This happens over time. And some things I saw during the lab were how voltage is distributed differently depending on each resistor's position within the circuit, and the amount of current flowing is controlled by the resistance of each component. Current and voltage values align with Ohm's law. Comparing measured data with theoretical calculations can make the experiment more accurate, and arranging circuit elements influences the total resistance and current flow, and altering resistor values affects current and voltage in the circuits. So for this experiment, the system was the electrical circuit that we're looking at, and the surroundings were everything outside of the circuit. We assume that the wire resistance is negligible and doesn't affect the measurements, and the ammeter's internal resistance is small enough that we can say it's negligible. So we created circuits and used voltmeters and ammeters, and then we swapped in resistors with different resistance values and compared experimental data with theoretical predictions using the laws we discussed in class. And we analyzed how voltage is distributed in the series versus parallel resistors configurations, and looked at how splits and flows through branches depend on circuit layout, and compared the overall behavior of the series and parallel circuits. So the first circuit, I calculated using Ohm's law, the current from that, and um, based on just like the laws. And then within the virtual lab, I found the simulated current, and I saw that the ammeter reading remained constant regardless of its orientation in the circuit, and replacing the ammeter with a voltmeter made a current reading of 0 amps. So this means voltmeters have very high resistance and block out the current flow. For the second circuit, I found that when the 10 ohm bulb is connected to a battery and capacitor, the light slowly dims and then it turns off. And when the capacitor is disconnected from the battery and connected to the 10 ohm bulb, the same effect happens. The light gradually dims and goes out. So in both cases, the current flowing through the circuit decreases and then hits 0. And this happens because in the first case, the capacitor charges up while the bulb is lit. As the capacitor approaches the full charge, the current decreases, and so the bulb dims and eventually goes out. And in the second case, the capacitor discharges through the bulb, and this makes light. And as the capacitor releases the stored energy, the current decreases, so the bulb dims and goes out. So in both setups, the current gradually drops to 0 as the capacitor charges or discharges. So the bulb fades out. So basically, through all of the analysis of what I did in this lab, the current through the original ammeter is unchanged. In a parallel configuration, current splits between available paths, and the ammeter placed in parallel with the 100 ohm resistor is a low resistant alternate path. However, the current loss ensures that the total current entering the node is conserved, and this means that current may redistribute between branches, but the total measured by the original ammeter before the junction doesn't change because of this. So then I created a linear model of the experimental versus hypothetical data, and it lines up like very similarly. So that means there's very little error, but it could have been from the simulation or through calculation. And so some potential ways that we could redo the experiment were if we were doing it in real life and used a real ammeter instead of an ideal simulated one, which could have added some more resistance And what if we were doing this in real life and used a real battery to charge a real capacitor with no resistor in the circuit? And how quickly would our ideal model predict the capacitor to reach full charge? So it would take longer, and with resistance, this slows down the charging process. Thank you.